Hi everyone, my name's Dan Crankshaw. I am a third-year grad student in the AMP Lab, and I'm going to tell you about some work we've been doing on serving machine learning models, serving predictions. So you've been hearing about the Berkeley data analytics stack for the last couple days. A bunch of great work. This is sort of a subset of everything that you've heard about. But fundamentally, a lot of this work is focused on creating data products. Those data products might be reports, or they might be sophisticated machine learning models, or they might be clean data. But basically, all of this work is taking raw data and in some form or another doing analysis on it to create some product. And this is awesome, but it's sort of missing a component. Namely, what do you do with those data products once you have them? How do you deploy them? How do you serve them? How do you turn them into real-world actions? And particularly, how do you do that in a scalable, performant, low-latency way? So I'm going to talk about a specific data product, machine learning models, which seem to be pretty popular these days. And I'm going to motivate it with an example. If you were here last year, this is the same example I gave last year. Let's say that I wanted to build Catify, a recommendation service, a streaming music service for cats. And I want to have sort of the best service because I need to outcompete Pandora and Spotify and Google Music and all these, and Apple Music now. So I want to have awesome recommendations so that I can sort of find the best music to play for all of my users, all of my cats. So I'm going to use machine learning. So the first thing I'm going to do is figure out how can I use machine learning to improve my service, to build the best music service out there. So I'm going to define my modeling task. And in this case, what I'm doing is for every user in my system, and all the users that I hopefully will come to my system once they hear how awesome it is, I want to be able to predict for all the songs in my catalog what that user would rate for that song. But there's some problems here. If every user rated every song they listened to, like maybe this wouldn't be such a big deal. But I have millions and millions of songs in my catalog. Most of my users haven't listened to most of my songs. So I'm missing a lot of this information. So what I'm going to do is I'm going to use a machine learning model to predict all of these missing ratings. And then once I have these ratings, I can use that to figure out what songs to play for my cats. So how am I going to infer all these missing ratings? Well, I'm going to start with some known ratings, some training data. And I can feed it into something like a Spark pipeline or a Keystone pipeline and train a model. Use all the standard machine learning stuff that you guys have been hearing about. I can train this model on a massive data set. And the result is some trained model, a Keystone pipeline or maybe a neural network that's sitting in storage somewhere. So now I have this super accurate model. I use the Berkeley data analytics stack to create it. But I need to do something with it. So to continue building Catify, I'm going to build my serving platform. And now I can use standard open source tools to figure out how to serve songs to cats. But now I've got this divide where I've got this really accurate model that tells me which songs to serve. And I've got this serving system that says, tell me what song to serve, and I'll serve it fast. I need to bridge this divide. So a sort of traditional way of doing this is let's figure out what songs to serve offline, and then tell that to our service. So one way I could maybe do this is, well, I have a bunch of users, and I want to figure out what songs to serve them, and I have a finite amount of songs. So let's just pre-compute this offline, compute this cross product, and now I have my model telling me what every user would rate every song. But there's a bunch of problems with this approach. So if I pre-computed my ratings, I could stick them into my serving system. But now I have this black box data that my serving system doesn't really know anything about. And that's going to lead to some problems. First, what happens if I get a new user that isn't part of this pre-computed ratings data set? I can take some sort of average standard way of, pretend every new user is the same, But very quickly, that's going to run into problems as these users start to differentiate themselves. Continuing with the problems, as my cats interact with the system, not only are they providing new training data as they skip songs they don't like, as they rate new songs that they've listened to and now really like, their preferences might even change in reaction to the songs that I'm playing them from my recommendation service. Basically, all of this is providing new training data that we would like to incorporate into our model to reflect the changing state of the world. And we can do that, but the latency of getting a new piece of data, retraining a model, and incorporating that new model back as I serve more predictions is really high. So what's wrong with this picture? The problem is that we have a serving system that can provide data, serve data at low latency, but the data it's serving, these predictions, are stale because it doesn't understand what's going on in this black box. And we have batch training systems that are optimized to train really large-scale models on huge data sets, but they don't provide serving, and they're not necessarily great at incremental maintenance. And we have to combine these two sets of systems together to provide a model management system, and so we end up doing it in ad hoc and brittle ways. So, in steps VELOX. So the goals of this model serving system that we're building are to provide low latency and fresh predictions. And we're going to do this by breaking this black box abstraction and coming up with a set of model-specific optimizations. We're going to take advantage of the fact that we're serving machine learning models, not just arbitrary data. And we're going to do all of it in a unified system to ease all of these training and deployment and serving problems and make it easy to deploy new machine learning applications. So if we take another look at this badass stack picture that you guys have been seeing all week, what's missing is that we have a bunch of systems to train models, and we need a management and serving component to take advantage of these trained models and deploy them. So VELOX fundamentally has two components. There's a model management component, which takes care of this sort of retrain latency problem. And there's a prediction service to provide low latency predictions for a range of models. So I'm going to walk through each of these components in a little bit of detail. But before I do, I want to give sort of a high-level view of how you might incorporate VELOX into an application. So VELOX runs, as a service on a cluster. It's a standalone Scala service that has integration with Spark, but isn't necessarily limited to you training your models in Spark. We provide personalized predictions as a service, and it runs on a shared nothing cluster, and we take advantage of some context to get a nice primary key partitioning of your workload. So now that you have VELOX up and running, to use it to power Catify, I'm going to put together some little front-end application that tells me, that sort of runs the web page, and when a user logs in, I need to figure out what song to play. So when Cat4 logs in, my front-end service is going to request a prediction. It's going to request what song should I play for this cat over a REST API. VELOX is going to compute that prediction, return a score that's going to tell the front-end service what song to play. And that's all going to happen at really low latency so that this whole interaction happens at interactive speeds. And then my front-end application can play the song. Now, as my user continues with their music listening session, maybe they listen to a new song that they really like and they give it a thumbs up or a high rating. Well, this is actually just more training data for the system. So VELOX also exposes a way to incorporate this new training data at low latencies. So when user 4 rates a new song, or whatever your feedback mechanism is, the front-end system can send that feedback, send that additional training data to VELOX, which will incorporate it into that user's model in real time. That means that you can do things like when a user skips a song immediately because they don't like that song, we can take advantage of that additional training data, update that user's model to reflect that new piece of information about the user, and actually use that new model to predict the next song to play for that user. We can do all of this at extremely low latencies. But we don't want to throw away all of the work in building these large-scale training systems to train massive, highly accurate models. So we're actually going to use Spark as well to do batch training. So when we decide that we need to retrain our models from scratch, and I'll get into what that means exactly, VELOX basically offloads this work to Spark or to Keystone or to whatever your favorite neural network training system is, in a platform agnostic way, essentially. Lets that system train the model, and then it takes in this new batch trained model to continue to improve predictions. So first I want to talk about how VELOX serves predictions. So we have this simple prediction API where you can either ask for point predictions, point queries, like for this user and this song, predict the rating, essentially. And you can also ask for more complex ordering queries for recommender systems, like what are the top 10 songs that I should put in this playlist for this user. These predictions are personalized. Two different users with different interaction histories requesting a rating for the same song are looking at different predictions. And we use intelligent caching and some partial state reuse and smart materialization to make sure that all of this happens fast. So when a prediction request comes in, the first thing we do is we look up that user's model. We're doing personalized recommendations or personalized predictions here. So every user has their own model. And we make sure that we take advantage of the fact that every request is associated with a specific user. So every feedback request and every prediction request as a user associated with it. So we treat that user ID as the primary key to more efficiently lay out our models. The next thing we have to do is we have to compute the features for that input. Now this feature computation, particularly if you're taking advantage of things like the latest and greatest in large-scale models or pipelines, can actually be pretty costly. It can be so costly that it will make you miss your SLA and basically make prediction serving, take prediction serving from interactive to non-interactive latencies. So one way we alleviate this is we do feature caching at a feature level. Now the features for a song are going to be independent of any specific user. The prediction is going to take into account these features and that user's weighting of the features to provide a personalized prediction. But we can actually cache these expensive computations across users. But there can be cache misses. We won't be able to do that for every user. So we're exploring some techniques to provide predictions that are pretty accurate even while missing some features, and some ways that we can improve the cache hit rate by taking advantage of similar items, essentially. Once the prediction has been computed, there will always be a prediction return at low latency. We'll return the score, the predicted value, and the front-end application can use that to figure out what web page to load. Now I want to talk a little bit about the model manager, and this is really where the heart of the research in VELOX takes place. So a model in VELOX is actually two components. We decompose a model into a set of shared basis features, these shared feature functions, and we cache at this level. Now these shared features are trained on massive data sets, and as a result of that, they're not going to change very quickly. A few new training points added to a terabyte of training data are just not going to affect things. And so because of this, we train these shared feature functions, these shared models, in batch. Now to get personalization, we had a per-user ensemble model of these features. Now these per-user models are trained on small data because the amount of interaction or the amount of training data that any given user has is pretty small. And as a result of this, these user models can change quickly. And that's actually a good thing because, as we all know, our tastes in music and our preferences actually can change quickly as well. And because of this, we want to train online. This is the retrain latency that we really care about, is adapting to changing user preferences, to new users, to this dynamic world that we have to live in, or get to live in, I guess. So putting this together, when we get an input song, an input that we want to make a prediction about, we first feed it into our feature models, and these are going to give us rich features, rich signals about this input. Then we feed this small set of highly indicative features into this per user model, this per user ensemble, that's going to give us an individual weighting of each of these signals to provide a personalized prediction. Now, if we want to make a prediction on the same input, but for a different user, we're going to expect to get a different result. But what we can do is take advantage of the fact that the bulk of this computation is actually the same. The shared feature computation, that's the evaluation of your deep neural network. It's trained on a massive data set. And that's the part that's costly in prediction computation. So we can reuse most of this and just send these same features to the different per user weighting. That's just a dot product. It's really cheap. And get out a different personalized prediction. Now we can actually decompose this a little bit further. While conceptually there's sort of a user or a feature model, really this could be an ensemble of different models. Maybe different competing models that different teams developed, or models trained on different data sets, or even at different times. And to the system, it doesn't really care about this difference. It's all just ensemble models when we get to the per user model. So putting this together, what we get is a set of feature models that basically VELOX treats as expensive black box computations. This lets us have a really general view of what a feature function is. We can use features trained in different systems, with different formulations, with different speeds. And we rely on these to basically give us really high fidelity signals about the input. So this is just some set of features that produce basically a vector that we then can weight on a per user basis. So this per user model is this simple linear model that when basically multiplied with these high resolution, high fidelity features, gives us a personalized rating in a relatively efficient way. So when we talk about online updates, we're going to talk about updating this W, this per user model, which changes quickly and is trained on small data. And it's the observation that we can train these models on small data sets, and they're relatively low dimensional, that lets us train these Ws and reduce the retrain latency to literally milliseconds, to interactive latencies. So when we get some feedback, basically another piece of labeled training data that says, for this user and this input, here's the ground truth score. We're going to use that for online learning directly in the serving system to continuously update just that user's model. It's a small data computation, so it's pretty cheap, and we can afford to do it in the serving system. Now, we also want to save that data because eventually we want to retrain, or maybe we want to train a new feature function, and we want to use all the training data available to do that. And then finally, we can use this feedback to continuously assess how well our models are performing in production. So when a feedback comes in, and we want to update the model in real time, we look up just that user's model, we retrain it using things like stochastic gradient descent or some techniques in incremental linear algebra to make this computation really, really cheap. And then we save that result and can now use it to make predictions. And then when a developer decides that these feature functions are out of date, or a new intern comes in and says, hey, I know all about deep learning, or I know about this cool new Keystone project. I think I can build a better model than what you guys have right now. I'm going to train my own. They can use all the training data that we've saved across all the users to train this model offline in a batch system, and then deploy it as an additional feature or as a new feature in VELOX. So the advantages of this are that we can leverage all this work over the past decade plus in large-scale training. We can leverage different training systems for different feature functions. Some of these might be amenable to incremental updates, and we might want to use a streaming system to keep these feature functions as up-to-date as possible and sort of have a continuous deployment method, whereas others might be a massive complex neural network that takes 2 weeks to train and we can only afford to do once a year. And we can also have automated retrain policies on a per feature function basis. Now, I've talked a lot about recommender systems as sort of my running example, but really this approach is much broader. It can be used for sort of other applications of machine learning in production, like spam or anomaly detection or fraud detection. And this concept of personalization actually goes beyond people as well. We can use it for device or location-specific modeling. If I have, say, an IoT application or a manufacturing application, and I want to have a model for every machine in my manufacturing plant, I can use the same personalized approach. And we're also investigating ways that we can extend this model splitting, this model decomposition, to actually deploy models across a network. So maybe part of the model exists on your phone, and it's being trained locally on your phone, maybe even on sensitive training data that you don't want to upload to, to some big cloud provider servers, whereas the heavy lifting is still going on in the cloud that can leverage all the cluster computing resources we have. So to wrap up, VELOX is this missing piece in the BDAS stack that adds management and serving capabilities for these great machine learning models that BDAS can create today. And we need this because model training and serving right now rely on ad hoc and often manual, brittle processes that are spread across a bunch of systems, none of which were really designed to serve models and to incorporate this low retrain latency. So VELOX is going to automatically maintain these several personalized models and use them to provide low latency and accurate personalized predictions. We have a web page that is sadly a little bit out of date. And I have some time for questions now, but you can also feel free to send me an email if you have follow-up questions after this. Thank you.
Any questions? Yeah, I think everyone wants to go to lunch. Okay, yeah, there is one.
I can't hear you.
He's asking the website is out of date. How out of date is it? Like, can you please repeat the question?
Well, there was a big paper deadline yesterday, and we just submitted a paper with a bunch of new work and new results that are not on there yet. So the last 3 or 4 months of work are still in the pre-publication abyss of academia. But other than that, yeah.
Okay, let's thank the speaker one more time.
All right.